So, lecture 11, part 2, we're starting at 11.5 with things you should know. Previous to this, on the previous episode of Mr. Bennett Lectures, you learned about bond energy values and how to figure out in a chemical reaction how much energy is gained or lost by looking at a chemical reaction, looking at the bonds broken. But now we're going to see experimentally how we can measure the amount of energy given off or absorbed in a reaction. So we do this by using calorimetry. And this is using the equation Q equals MCAT. So, whoops. Okay, so this is what calorimeters look like. This goes from what we learn about in the AP Chem classroom. We'll use calorimeters like this, which is just like a styrofoam cup, to what you might see at a nice college lab. And then what you might see in industry. By industry, I mean like for-profit corporations. Now, what is the difference between the AP Chem classroom and the nice college lab? Money. The AP Chem classroom is not as accurate. Why might this be more accurate? Yeah, this retains heat better. We have stirring, so it keeps the temperature equivalent throughout. Anything else that... And then here, everything is digital. Right, so that's like a whole nother level of fanciness. So what happens is, and this is how, like, if you look at, so a Coke bottle, I'm going to say because it's right there, you can figure out how many calories there are by reading that on the label. But this is actually how they figure out how many calories are in food. You combust it. You actually burn it, you ignite it, and you figure out how much energy is released. Because essentially when you take in food, that's what you're doing. You're combusting the food, right? You're reacting it, and you're going through cellular respiration, all these things. So this is how they turn food into calories that are on your bottles. Now the thing with the calories on your bottles is it's a big C calorie, and for every calorie that it says there. So for example, Avery, how many calories are in that 20-ounce Coke? 240. I was going to say 240. I drink far too much Coke. So it's not like you're drinking 240 calories. You're actually drinking 240,000 calories. But we like using smaller numbers, right? So our 2,000 to 2,500 calorie a day diet is actually 200,000 or 250,000 calories per day. But we wouldn't want to talk about it in that terms. We could just say kilocalories, but for whatever reason, this has just become the convention. And it's measured using calorimetry. All right. So, oh, wait. Is there a slide on yours that's not here? All right, let's put that in. So we have Q equals MC delta T. What does delta T mean? Change in temperature or difference in temperature. Yeah, this blank slide isn't on your sheet. It's, as yours, it says calorimetry strategy. Yeah, you can just put it underneath. All right, what is the C equal to? Let's see if you remember your freshman physics. Ah, so it could mean the speed of light, but not in this case. Specific heat. I love that being the speed of light, though, because you get some enormous numbers. All right, so M, mass. And then Q, because we like being difficult, heat. Heat. So the heat gained or lost is based on the mass times the specific heat capacity times the change in temperature, where delta T equals TF minus TI. So the sign of Q is important. Those are some ugly, ugly exclamation points. So what do I mean by that? If Q is less than 0, what does that mean about my system? Okay. Yeah, exothermic, it gave off heat. And Q is greater than 0, it's endothermic. So from part 1 of this lecture, we talked a lot about endothermic and exothermic. So, and we talked about doing bond reaction energies by looking at the bonds broken and made. This is how we would actually do it in the lab. Okay, so what we're going to do now is a calorimetry example. I want you guys to do it with your tables. While I rest. Okay, so let's chat. There were 2 questions. One will come up a little bit later, but the first one, can temperature stay in degrees C? The answer to that is yes. Here's why. The difference between Celsius, 2 Celsius values, is the same as the difference between 2 Kelvin values. Because remember, you're just to go from Celsius to Kelvin, you're just adding 273. And if you add 273 to both your initial and your final, the delta is going to be the same. So it can stay in Celsius. The other is the convention of energy released, and we'll talk about that in a minute. So we want Q equals MC. Bless you. Okay. So what did you guys get for the M for this? M equals 100 grams because mass equals density times volume. Density is 1.00 grams per ml times 100 milliliters equals 100 grams. C is 4.2 joules per gram degrees Celsius. And delta T is equal to 6.8, 5.8. All right. So we multiply these together. Here's one way that the units here can get messed up. Your C can be in different units, your mass. So I like keeping my units straight and just making sure I'm in the right spot. So Q should be in joules. So 100 times 4.2 times 5.8 is equal to what? 2,436 joules. Now, yeah, Masha. Shh. So the question is, would I like you to show all your work? Here's the thing. If you just put on a test or quiz 2,436 joules, you'd get full credit. But if you made a math mistake, which I see from time to time from people, then you'd get 0 points if you just wrote down the wrong answer. But if you write down the whole process, like the way Mr. Hamill and I grade is if this is like a 4-point problem, +1, +1, +1, +1 for the final answer. So you'd get 3 out of 4 if you set the whole thing up. All right. Yeah, Eli. So significant figure says that this should be, I think, 2440. Oh no, it should be 2400 because we have the 2 sig figs from the temperature. But we're not going to worry much about sig figs moving forward. Yeah. No, so the question is this the math we're talking about? No, it's much more complicated than it, but not much more, but somewhat more complicated. Yeah. Other questions about this, and then we're going to get to the question Davis and Kenny asked in the back. Okay, so, oh yeah, Owen. These are not the maths you are looking for. So one of my like big dad moments that I'm waiting for is when my kids are old enough to watch Star Wars with me for the first time. I'm like holding on to that. Like I can't wait. But I haven't decided the order yet. There are some people who say you should go 4, 5, 1, 2, 3, 6. Okay. Or 4, 5, skip 6 and not. My biggest like this is something that I'm really scared about is that my kids will like the 1, 2, and 3 more than 4, 5, and 6. And if they did, I might have to disown them. I could. I'd be like, these movies are awesome and those are terrible. If you, oh yeah. Well, they'll still be young enough that they might actually respect my opinion at that point. All right. Now, the question is, it asks how much is released by the reaction. Here's where sign becomes important. Now, the sign here is positive because water, this is key idea, like big flashing big idea. Water absorbed energy. So the reaction was exothermic, but to the water was endothermic because the water took in the energy from the reaction. So this reaction between hydrochloric acid and sodium hydroxide was exothermic. It released energy, the temperature of the water went up, right? So if it asks you how much energy is released from the reaction, you would say 2,400 joules. If it asked you for the delta H of the reaction, sorry, you guys don't know delta H yet. So if it asked you for the change in energy of the reaction, it would be negative 2,400 joules. So there's a difference between, you have to watch your wording. The reaction released 2,400 joules of energy. The change in energy for the reaction was negative 2,400. Okay? The potential energy went down, it released energy, so it lost 2,400 joules. Does that make sense? The biggest thing that students have problems with this kind of calorimetry is that sign. If the temperature of the water goes up, that means the reaction was endothermic and released energy. If the temperature of the water goes down, that means the reaction was endothermic and absorbed energy from the water. So be careful with your signs. All right. Now, I don't know if kids these days, I don't know if you guys still say this, but back when I was younger, we used to say like, oh, that was the bomb. No, it is. This is actually a thing, a bomb calorimeter. But I liked, every time I read it, I giggle because I'm like, oh, that's the bomb. So your lab just bought a new bomb calorimeter. So here's the thing with the bomb calorimeter. It's called, I'm not sure, but it might be called a bomb because it looks like it's like a big, huge metal piece. Before it can be used, you need to determine its total heat capacity. So the difference between a bomb calorimeter and a normal calorimeter is that I can't get through this sentence without laughing. But the bomb calorimeter is the mass. It's a total heat capacity. It's not a specific heat capacity. So you notice the units that you need to, this is C, but your C is not going to be joules per gram degree Celsius. It's just joules per degree Celsius. The mass is already taken into account. So the mass of your calorimeter is already taken into account. So you place a 0.182 gram sample of benzoic acid and burn it. The temperature raises by 1.22 degrees C. Benzoic acid is known to release 26.4 kilojoules per gram when it burns. What is the heat capacity of the calorimeter? So the difference is, and I'm going to see if you can figure it out. The difference of your units of C are joules per degree Celsius, not joules per gram degree Celsius. See if you can figure out what that C is. All right, so I'll leave you guys where you are because I think this is confusing. I don't think I gave you enough structure for this. So the first thing you want to do is the energy released by benzoic acid. I'm already on the next page. Okay, so we have it'll be okay. All right, so 1.82 grams, 2.64 kilojoules per 1 gram. So when I talk about the math that you guys are going to have to do, it's math like this. It's more ratios, like setting up ratios, watching your units, going through canceling units, and getting things like this. So what do I get when I multiply 1.82 times 2.64? Like, except it's 0.1. So what do I get when I multiply that? 4.80. Now, yeah, 0.4. What was it, Alex? Just move it one decimal. 480 kilojoules. Now, it says it releases that much energy. So this should be a negative, right? If I burn 0.182 grams of benzoic acid, the change in energy is 0.48 kilojoules. Okay. So now I have, if that energy is released, where does that energy go? It goes into the bomb calorimeter, right? So you flip this sign, so 0.480 kilojoules absorbed by calorimeter. So now see how my sign flipped there? It was negative when it was released. So the reaction released the energy. The calorimeter absorbed it. So 0.480 kilojoules is equal to, did anybody get this step right here? Yep, which is, oh, okay. 1.22. So look at, here are your units, right? Joules and degrees Celsius. I mean, you're going to get something like 0.4. Yeah, you can keep it in kilojoules. All right, 0.394. This is your C. So for a bomb calorimeter, we're not going to talk much about bomb calorimeters, but the equation is Q equals big C delta T, where this is no longer specific heat capacity. This is the total heat capacity. So it's like when you have the total heat capacity, it's like you're multiplying the mass times the specific heat capacity already. Damn it. Yeah. I'm going to see if I can do it this way. All right. 26.4. Thanks, Cameron. 4.8, 4.8, 4.8, 3.94. So the bomb calorimeter may actually be, so the question was, what will the readout be? The bomb calorimeter might, depending on what the programming is for it, it could tell you the change in temperature. It could tell you the energy absorbed. And if it was really fancy, you could input the mass or the moles or whatever, and you could get the energy released by your reaction. Yes. So you're measuring the change in temperature of the calorimeter itself. Normally, you're going to be measuring the change in temperature of water, because most reactions take place in water. But with the bomb calorimeter, you measure the total that the calorimeter went up. So like when we do calorimetry, we lose heat to the environment, we lose heat to the cup, like the styrofoam cup. So it would be like if you sealed the styrofoam cup and had the same amount of water in it all the time, and then you can measure the total heat capacity of that system, right? Okay, so the last little bit, and the question, oh yeah, Eric, go ahead. Yep. Mm-hmm. The question was, why isn't this MC delta T? It's because it gave you the heat released in kilojoules per gram, right? So in the reaction, if you burn 1 gram of benzoic acid, you'd release 26.4 grams. So it's not an MCAT question, it's a heat of reaction question. So I'm telling you, a lot of what you will have seen, whatever the grammar is from that, from the first part of the lecture, talks about the energy in reactions, and it gives it to you in kilojoules per gram or kilojoules per mole, and then you can figure out how much energy is released by multiplying by the grams or the moles or whatever. Here we're looking at calorimetry in this second step, which is Q equals MCAT. So you can figure out, in this case, I gave you the energy released. All you need to do is multiply the energy of the reaction times the amount that you had. All right. So the question was, you might notice that there is no page 5. That's okay, because all page 5 is are the objectives, which you already have. So work. Things you should know, 11.4. Energy can be transferred from one system to another by heat, which is, we've already talked a lot about this, right? It's been a question on a couple of your tests, like test 1 in the cumulative, I think, where transferring energy from molecules bumping into slower moving ones, right? Fast ones transfer to slow moving ones. Actually, this should say, more specifically, higher KE to lower KE. Most of the time that has to do with velocity, but, or by work. So we're going to talk now about work. So when a gas expands, it pushes outwards on its surroundings. That's doing work. There's not a whole lot that you're going to be tested on in regards to work. In fact, Mr. Hamill and I are still trying to figure out exactly what level of depth the AP curriculum wants us to go into it. So you're just going to get like, this is going to be one of those sort of like hand-wavy things, a quick intro to a much more difficult concept. So work. We're generally going to look at this as work equals negative pressure times the change in volume, where delta V equals V final minus V initial. Now, where this gets conceptually difficult is thinking about how the work is being done. So generally, in order to change volume at a constant pressure, and I have a gas, what would need to change? Oh, that's a terrible question. I apologize. That was just an awful, awful question. So how can I change volume? Right, so I can change the pressure, change the temperature. Unfortunately here, I can't do either of those things. So I am just actually going to expand or contract a gas. Now, that seems strange, that I'm not doing anything else to it. This can happen during a chemical reaction where, like combustion, this can happen. You can do work from combustion. And thankfully, we can do work through combustion, because what do we get out of that? Like moving cars, right? Moving cars and power plants and stuff. We are, on your problem set 11, you're going to have a whole thing about how a power plant works and like where the heat is going and where the work is going. It's one of my favorite questions of the year, just because it's actually applying what you guys are learning to like real life stuff. So expand or contract a gas is when you have work done. So for example, if I put a block, so there's not a lot of great examples, but mostly we're going to think about it in terms of pistons. Pistons moving up or down, because that's how we harness work. That and turbines and things like that. So if I press down on it, I'm doing work. If it presses up on me, work is being done to me. So all we're thinking about is changing volume. And that's how we get work done. Okay. What is the direction of work? if work is done by the system. That means work is going to be less than 0. If you think about work the same way you think about energy, and work is being done by the system, so you're using that work to get energy out, that means energy is leaving the system. So whatever your system may be, like your piston, right? So here's an example. Before and after so something happened between here and here. Whatever gas there was inside the piston pushed up and moved it, right? If this gas does work and pushes on the piston, what about the energy of that system now? Did it give up energy or did it get energy in? It gave up some of its energy. In order to do that work, energy is required. So that's why we say the work is less than 0. It's losing its energy to do work. Conversely, if work is done to the system, the work is greater than 0, and this is the opposite. So here you can think of it as, in order to move that piston down, somebody or something had to push it down. Or the gas had to contract on its own for some reason. So if I am someone who's working on a piston and I push it down, I'm doing work to the system. I'm increasing the amount of energy stored in that system now. So this is what we mean by direction of work. All right, last 2 slides, and then we're done with lecture 11. Very short lecture. I give people a few more minutes to draw their beautiful drawings. Does anybody need me to wait? Okay, at your tables, how much work in joules is done when a piston expands from a volume of 13.27 liters to 76.55 liters against this pressure? So how much work in joules is done? So you need another conversion factor. Okay. So what did we get when we multiply 14.89 times 63.28? I don't have it in front of me. Kenny? 942.24. And that's going to be negative in this case. So then we multiply it by 100, right? And then if we want it in, oh yeah, we just want it in joules. So you should get negative 9.42 times 10 to the 4th. Yeah. All right. Now, here is where we have to worry about the sign. It says how much work is done when a piston expands. So it is expanding. The total work of the system is negative, but the amount of work being done is 9.42 times 10 to the 4th. It's doing the work on the piston. So we'll put this all together on the last slide. Combining W and Q. Hold on one second. I want to get this. Actually, that's not the way you'll see it written. You'll always see it written the other way. Now, E is the total energy of the system. So the total energy of the system is equal to Q, which is the heat, plus W, which is the amount of work. So we're generally going to be looking for changes versus absolute. When you get to thermodynamics in college, you'll do absolutes. But for now, we're looking at deltas. 99% of the time in this class, well, maybe 97.5% of the time in this class, we're only going to worry about Q. Right? We're not going to be measuring the energy of systems with changing volumes. We don't have pistons in here. Maybe if you go down to engineering, they might have some things that you could play with to measure the work done by a system. But for us, we're really going to be focusing on Q, which is the heat energy absorbed or released by a reaction. We'll talk about W on the problem set. Maybe you'll have one test multiple choice question or something, but not a whole lot of talk about W. Okay, done.